Let's work on solving some trigonometric equations. We're going to rely a lot on the skills that we've learned already in this class. So we're going to have to remember our unit circle or special triangle values. We're going to have to rely on a lot of the identities that we've been working with more recently. We're going to have to rely on some of the formulas that we've been working with. So we're going to bring in a lot of old knowledge. We're just putting it to a new use. So let's start off nice and easy. Sine x is equal to negative 1/2, and we want to solve this equation. Well, we know when sine x is equal to negative 1/2. Sine is equal to a 1/2 at pi over 6. But because it's negative, we know that sine is negative in the third and in the fourth quadrant. So we need to take that pi over 6 and put it into those quadrants. And so if we think about going past the x-axis by pi over 6, that would mean we have an angle of 7 pi over 6. But that's not the only place. Sine equals negative 1/2 in two places, also in the fourth quadrant. So we think about coming back from 2 pi by pi over 6. That would be 11 pi over 6. And those still are not the only two answers, though, because we know how coterminal angles work. Anytime we have any coterminal angle, that also has to give us the negative 1/2. So I'm going to do to represent that we have that infinite solution set. I'm going to put plus 2 pi, because we can add, subtract 2 pi as many times as we want, and indicate that we're doing it over and over again. I'm going to attach an n to it. I do that in both of my solutions. And what that n is just any integer. That allows me to take as many rotations as I want around the two initial points that I've given. So these two initial points are true, but then I can add, subtract 2 pi as many times as I want. N is both positive and negative, but being an integer, we have to stay adding and subtracting 2 pi's. Let's take a look at another one, but this time let me change the instructions a little bit. From here on out, what I'm going to do is I'm going to solve the equation on the interval 0 inclusive to 2 pi non-inclusive. So what that's going to do is it's going to limit my solution set. We'd only have these two initial solutions. I don't have to worry about putting that plus 2 pi in. Both are valid things that we'd want to do. Sometimes we want to have all those solutions. We don't want to restrict our interval or solution space. But there are times that we only care about those initial solutions as well. That should be a parenthesis, not a curly parenthesis. So 0 inclusive, 2 pi, parenthesis non-inclusive. Let's take another example. This time I'm going to have the equation 2 cosine x minus root 3 equals 0. So this is of linear form. We only have that single x. It's clearly not a linear equation, but it is of linear form. We only have that one x term, so I'm going to work to isolate this x term. That requires me to add the root 3 over first. I need to continue to isolate that cosine x, the factor with the x in it. So I'm going to divide the 2 over. Cosine x is equal to root 3 over 2. And we know that occurs at pi over 6. And also in the fourth quadrant, so the 11 pi over 6. Two different solutions this time. I'm not going to put the plus 2 pi in like I did last time because we've restricted our equation to being on the interval 0 to 2 pi. So those are our two answers. There are times that I will have to say, hey, there could be a plus 2 pi in there. I need to track that 2 pi in there. So let's look at an example. Let's take sine of 2x is equal to root 2 over 2. Well, we know when sine of 2x is equal to root 2 over 2. That is true at pi over 4. It is also true in the second quadrant at 3 pi over 4. But I'm not just going to stop like I did last time, because last time we just had an x in that variable position, or in the angle really. Here we have a 2x in our angle. And so I haven't finished solving, right? I found when sine is equal to root 2 over 2, but that just is what my angle is equal to, not the x. Same thing over here. I'm going to put my 2x is equal to my 3 pi over 4. And so if I were to divide over the 2, that would be the correct logic. I'd get pi over 8, but the problem is I've missed something here. There's something else going on. Let me put that plus 2 pi in there for just a second. So if I were to divide the 2 over to isolate the x, I would see I still get pi over 8, but then I have to add to that pi n. Before I didn't bother putting that plus 2 pi in there because if that 2 wasn't there, x equals pi over 4, I can't add 2 pi to it and stay between 0 and 2 pi, which is my desired region. But because we had that 2 in front of it, when I divide that 2 over to the other side, I have pi in. So I get the initial solution of pi over 8, but then I can also add pi to that this time and stay between 0 and 2 pi. 9 pi over 8 is between 0 and 2 pi, so that is another valid solution. If I look at this second equation over here to the right, I'm going to do the exact same thing. I'm going to put the plus 2 pi in there. So when I divide, I get x to be 3 pi over 8. But I also get a second possible solution because I can now add pi as many times as I want and stay between 0 and 2 pi. And so I get the solutions of 3 pi over 8, and I get 3 pi over 8 plus 8 pi over 8, or 11 pi over 8. Now, why am I stopping there? Well, on both of these, if I take 9 pi over 8, add 8 more, that'd be 17 pi over 8. That's too much. I've added 2 pi to something that started greater than 0. It'd be too much. If I take the 11 pi over 8, add another 8 pi over 8, again, it's too much. So we have 4 solutions. Now, there's a way I could have kind of predicted that. If I look at the initial equation, I know that sine is equal to root 2 over 2 in 2 different places. We said that at the beginning. If we think about what this 2 does, this is influencing our period. This would be like taking our period and dividing it by 2. So now our period is only pi. If we think about the standard sine graph, that would be one wave where it ends at 2 pi. Well, if we just compress the period by a factor of 2, that means I'm going to end up with twice as many waves in that region. That's a rough sketch. I didn't hit my marks exactly, but I'm going to have twice as many waves in that region because I've condensed that period in. It's happened a little bit faster. So that root 2, we can now see that we end up with 1, 2, 3, 4 different places that occurs. These are just ballparks, little green slashes of where they would occur. 4 different solutions. So on that first example, we put the plus 2 pi in there because we have to have it there. We didn't restrict the interval. We said, hey, anything works, and so we have to have all the solutions. On the second one, because we were solving on 0 to 2 pi, we got those 2 initial solutions, and we don't have to bother putting the plus 2 pi in there because if I add 2 pi to these, they're going to be outside the interval. The third one, the second we do anything to the angle, if there's anything inside that trig function, we've got to start tracking that plus 2 pi in. We've got to put that down because we're going to have to modify that in some way. It doesn't matter if it's sine of 2x, sine of 5x, sine of 1/3 x, sine of x plus 15. Anytime there's anything with that x inside the trig function, we've got to put that plus 2 pi in there because potentially we can add, subtract it, and get other solutions. I could have also subtracted, but notice I can't subtract in this case. That would give me a negative value. We've been using exact values, but we don't have to use just exact values. So let me switch over to tangent this time. Let's say that tangent of 3x is equal to 0.213. Tangent has an infinite range, so I know this is definitely a possible value. I need to find out what all the x values are. And so the first thing that I'm going to do is I'm going to say, when is tangent equal to 0.213? Well, I don't know this time because that's a non-exact value. I don't have a value in the unit circle or the special triangles that will give me that 0.213. So what I need to do is I need to take the inverse tangent. Take the inverse tangent of the 0.213. And when I do that, let's see what we get. And when I type that in, I get the answer of 0.20984. So very close to the initial number, just because anytime we're close to 0, sine and tangent both have the angle very close to the resulting ratio of sides, but just kind of coincidence, it looks nearly the same. So let's just round it. This is already rounded. There would be more decimal places. Let me just round it for simplicity to 2 decimal places. 3x is equal to 0.21. Now this is not the full story right now because what we just talked about, for one thing, I need to add 2 pi n anytime that I have an angle other than just the x. So here I have 3x. I need to keep track of that plus 2 pi n. But I'm going to go a step further. If I went to put 2 pi n, I could do that. That would be valid, but I'd have to go on to find the second place where tangent is equal to that 0.213. Remember, tangent is positive not only in the first quadrant, also in the third. If we use an inverse trig function, it's going to give us the one correct answer based on the inverse domain and range. But we weren't looking for when tangent, what the inverse tangent of 0.213 was. We were looking for the tangent to be equal to 0.213. So we know tangent is positive in the first and also in the third, so I'd have to pick this up and put into the third by adding pi to it. Well, because tangent's domain matches up with its period, I can just add pi in and I never have to worry about writing out that second equation. So I'm going to use 3x is equal to 0.21 plus pi n. Now, before I go writing out my solution set, I still need to get the x by itself, so I'm going to divide everything by the 3. And it's better to use your calculator to use exact values. I'm just going to write it out, and then I'm going to use my exact values and then my calculator to write out my solution set. So I have the 0.21 divided by 3 plus whatever I get when I add pi over 3 more. I'm going to keep adding pi over 3's until I can't anymore. So I'm going to write down those solutions and you'll see them in just a second. So when I list out my solutions, I get 0.07, 1.11, 2.16, 3.21, 4.26, 5.31, and that's rounding to 2 decimal places if you're close. If you're getting numbers that are close but a little bit off, keep in mind that I am using the exact value calculator, not actually what I wrote down. So I'm using the answer I got up here, dividing that by 3, and adding pi over 3 all in the calculator so I get exact values. So you try to use exact values as frequent as you can. Notice we get 6 different solutions. 5.31, if I were to add another pi over 3, that would be too big. I'd be outside of the acceptable 0 to 2 pi region. And we should kind of expect 6 solutions. We expect 2 typically for tangent, but with that 3 there, we've condensed the period in by a factor of 3. We're going to triple the number of solutions. Let's take another example. Sine squared x plus 2 sine x equals 3. We're back to x's, so we don't necessarily have to write down that plus 2 pi, and we're going to solve it on 0 to 2 pi again. But a little different this time. It's not of linear form. We have an x, but we also have an x squared here, or sine x squared really. It's not a quadratic equation, but it is of quadratic form, which means I should get it set equal to 0 and then try to factor it, or if I couldn't factor, I'd use a quadratic formula. So when I move the 3 over, I get sine squared x plus 2 sine x minus 3 equals 0. And if I were to factor that, I'd have sine x, and to get 3, one's going to have to be a 3 and one's going to have to be a 1. And if I think about which way the sign should be, I want the 2 to be a positive, so that tells me 3, I want to have a plus 3 sine x minus 1 sine x to get a 2, and that looks good. So now that I have it factored just like we do with any other quadratic equation, I'm going to set both of my factors equal to 0. And once I have them set equal to 0, I'm going to solve each of these equations the same way we were doing earlier. So I'm going to subtract that 3 over to the other side, or I'd add the 1 to the other side. This first one, sine x is equal to negative 3. I might say, well, that's not a value in my special triangle's unit circle, so I'm going to have to use my calculator, but I don't, because remember the sine's range is from negative 1 to 1? That's not in it, so we're not going to get any solutions from that equation. I'm going to concentrate on that second equation. When does sine x equal 1? Sine x is equal to 1 anytime our x is equal to pi over 2. And because I don't want to have values beyond the 0 to 2 pi region, I'm done. Anytime you have sine or cosine equal to 1, that is the one time that we only expect to have one solution. Sine only equals 1 at pi over 2. If we were to think about 3 pi over 2, it's equal to negative 1, that would not work. So I get just the one solution. All right, let's take a look at this next example. We have 2 cosine squared x plus sine x minus 1 equals 0. Now, before I jump into a trig function equation, I need to make sure that I have the same trig function and that the angles are the same. The angles do match, but the problem is the trig functions don't. So I need to get a way for these trig functions to match. Otherwise, I can't factor this to do anything with it. They're not going to simplify in any way. Easiest way to switch cosines and sines around is using the Pythagorean identity. So I'm going to change this cosine to a 1 minus sine squared. It is always much more challenging to change just a sine or a cosine. You would have to use a cofunction identity potentially, and that would change your angle. We don't want to change the angle. We want the angles to be the same. So it changes between sines and cosines very easily without changing the angle. Pythagorean identities. Notice I've left this cosine squared in parentheses. I need to make sure I'm distributing that too. So I'll get 2 minus 2 sine squared x plus sine x minus 1 equals 0. A little simplification, I'll have negative 2 sine x, sine squared x, then the sine x, and then 2 minus 1 will give me 1. And now we're to the same point we were just a second ago. I need to factor this. So it does factor negative 2 sine x. That's going to be a 1. Sine x. Now I might have that negative actually in the wrong spot. We'll figure that out in just a second. The factors of 1 are 1 and 1. So if I look at this right now, I'd have negative 2 sine x and a positive sine x. So I can make both of these negative if I want to. Or maybe the easier thing to do is just switch which one the negative is on. So I'll have it a 2 sine x and a negative sine x to get me to 1. And that way I can leave both of these positive. So you could have left that as a negative 2 and just use a negative 1, it doesn't matter. But either way we factor it, we get 2 sine x plus 1 equals 0, and negative sine x plus 1 equals 0. Now I'm going to solve both of these equations. So sine x will be equal to a negative 1/2, and sine x will be equal to a 1. Both of these are valid, unlike the previous example where we ended up with one solution. I can find solutions for both of these. When does sine x equal negative 1/2? Well, we already did that one, right? That was the pi over 6, which would give us 7 pi over 6 and 12 pi over 6. Writing and talking at the same time, they should both be over, not 12 either. Try that again. We should get 7 pi over 6 and a 11 pi over 6. Because we want to be in the third and fourth quadrant, ending up with a 1/2 would give me the pi over 6 as a reference angle. And then sine x is equal to 1 at pi over 2. We've seen all those solutions before, just not in this complex of an example. Let's do one final one. I think I'm on number 7. Let's take sine x plus cosine x equals 1. This one's the most tricky one that we've looked at so far because I have sines, cosines, and what we just said with the Pythagorean, there's no way for me to easily go between these two. I'm kind of stuck. I don't know what to do on this one, but what I can do is if I could end up with a Pythagorean, it would be very easy to change things around. In order to have a Pythagorean, I need to have sine squared and cosine squared. Now I can't just stick a squared here and here. I'm not allowed to just square individual terms, but what I can always do to an equation is I can do the same thing to both sides. So I'm going to square the left-hand side, I'm going to square the right-hand side. When I do that, I'm going to have sine squared. That was our desired outcome, to be able to change them around a little bit easier. Unfortunately, we end up with a 2 sine cosine, because we have to remember to fully distribute this polynomial or this binomial out, and that's going to give us that middle term. And then we're going to have a cosine squared, and this is equal to 1. So it seems like we're kind of stuck again. We're back with sine and cosine, but sine times cosine is actually really nice, especially when there's a 2 in front. This is our double angle formula for sine. This is sine of 2x. Sine squared very easily changes to 1 minus cosine squared, or we could just say that sine squared plus cosine squared is equal to 1, still equal to 1. So now I have just a linear form of equation. I can isolate the sine x and get sine 2x equal to 0. So we have that double angle on there. We're going to have to concentrate on those 2 pi's. We're going to have to add those 2 pi's back into our solution set, but let's list out when sine is equal to 0. That is true at 0. Should be 2x is equal to 0 plus 2 pi n. It's also true at pi, so pi plus 2 pi n. I need to isolate my x, so I'm going to divide by 2. Well, 0 divided by 2 is still 0, but then I have a plus pi n. I need to remember to divide both of those terms by the 2, so that's why we get the pi n. The second one, we get x to be pi over 2 plus pi n. So if we start writing down all of our solutions, we get 0, we get pi from the first equation, we get pi over 2, and we get 3 pi over 2 from the second equation. And up to this point, I've always just circled this, called it a day, right? There's my answers, I'm done. I gotta be a little bit more careful on this one. I told you this was the trickiest one we've done. We can always check our solutions by plugging them back into the initial equation. And we haven't bothered to do that up until this point because they've been right? We end up with those correct solutions. The trick here is we changed the equation. We started out with an equation of linear form, an x plus an x of linear form, and we chose to square it. And that's mathematically legal, but we have changed the type of equation that we have. We've changed it into a quadratic form, or we've significantly altered its structure. And we've seen this before. Anytime we alter the structure of an equation, for instance, the absolute value, if we drop those absolute values, we have to check the solution. We have a rational equation where we have something in the denominator. We multiply by the thing in the denominator, but we have to check those solutions. I'm going to have to check these solutions in my equation. So let's think about what happens when I plug the 0 in for my x. Sine of 0 is 0. Cosine of 0 is 1. That one checks out. Next, I'm going to take the pi and I'm going to plug it in. Sine of pi is 0. Cosine of pi is a negative 1, not a positive 1. We're supposed to have started with that positive 1. So that tells me pi is not going to work. Next, we'll plug in the pi over 2. So if I plug the pi over 2 in, sine of pi over 2 is a positive 1. That's good. Cosine of pi over 2 is 0, so this is 1 plus 0. That's going to work. Then finally taking the 3 pi over 2. Sine of 3 pi over 2 is negative 1, that's a problem. And then cosine of 3 pi over 2 is 0, negative 1 plus 0 is being negative 1. That does not work. So the only solutions that we want on this problem, we have 0 and we have pi over 2. You can always check your equations, but if you are changing the structure of the equation, if you're squaring something or dropping absolute value or anything like that, multiplying out by a denominator, we've got to remember to check those solutions. Potentially we've affected the solution set. When we squared it, we're leaving off the fact that we don't want negatives. We didn't want a negative at the beginning, so we have to eliminate those negatives at the end. So this was an example where we used a couple of different identities. Well, we used an identity, the Pythagorean identity, and double angle formula. We have to remember all those formulas and all the identities. They're all going to help us when we're solving these trigonometric equations.